Okay, so the book just mentions carbon cycle modeling, but then I took it and added further details at this point of this series of podcasts because I figured this is as good a place as any to raise some of the carbon cycle modeling issues. And now climate pretty much cannot be talked about without talking about carbon cycle, because we have been emitting so much carbon by burning fossil fuels and of course cement and steel production and land use change, urbanization, deforestation, agriculture, etc., that including the carbon cycle becomes very important, especially even if you want to look at seasonal time scales sometimes, or especially longer time scale projections into the future. So you will find thousands of cartoons, schematics of the carbon cycle. I'm starting with the one in the book which says the largest climate system reservoirs include the deep ocean, where carbon and heat can stay for a long time through the thermohaline circulation, for example, that we talked about, and the sequestration of carbon that sinks out of the circulation into the sediment. Soil and vegetation also are significant sinks. The surface ocean and the atmosphere, of course, are involved. The approximate size of exchanges or fluxes between the boxes is given by the width of the arrows. Red arrows indicate perturbation by human beings. So just look at the stock sizes or reservoir sizes. These numbers keep changing quite rapidly because every year we're increasing these. You can think of this as basically twice the concentration of CO2 in ppm. So we are around 420 now, so this number should be up to 840 gigatons. So this is the amount of carbon in each reservoir at 10 to the 9 tons, which is a gigaton. So biota have a small amount because it's just a seasonal growth and demise, but deep ocean stores 37,000 gigatons compared to this reservoir here, which is so small. Surface ocean has 900. Human beings are perturbing the ocean sources and sinks, as well as the export of carbon and burial here into the sediment, for example, by cascading effects. And we have respiration, fixation, and vegetation and soil reservoir of 2400 gigatons with these fluxes in and out. Human beings are perturbing these as well. And of course fossil fuels estimates, there are so-called producible estimates and resources, where resources are theoretical estimates which can be 10 times or orders of magnitude higher. So fossil fuels 3700 gigatons, again these numbers differ in different schematics you might see. We're extracting them and putting them out into the atmosphere, which then has to find its way into these reservoirs through these processes. So that's one of our biggest perturbation, as you can see with the thickness of the arrow here, and these are of course large as well. Okay, so modeling then includes details of these flows through the system. So this is from the Berkeley site. This kind of information is available at NASA site, NOAA site, UCAR site. So I'm just copying all the sites, but this Berkeley site here should be able to give you this site here should be able to give you all these figures I'm showing here. So you can see here that we are of course most worried about the greenhouse gases and the processes, right? So there's atmospheric dissolution and ocean uptake, which leads to ocean acidification. If the increase in atmospheric CO2 is faster than how the ocean equilibrates, there are details there which are in the carbon cycle course that you can look up. And CO2 is of course taken up for photosynthesis on land and in the ocean, productivity and biomass, and ocean buries some amount and so does land. So all those processes have to be modeled. Then there are processes like fire, natural wildfires, and then the question is whether with climate change these fires are changing in duration, frequency, intensity, areas burned, and so on. So photosynthesis, respiration, productivity, and biomass similar to ocean. Burning of fossil fuels here, of course, we are extracting and burning it, and we're also releasing it through agricultural activities. Volcanism and deforestation and reforestation are sources. This is a natural source. This can be natural due to wildfires, but of course human beings are perturbing these seriously, as indicated by the red colors here. So weathering and erosion have to be modeled if you want to model a carbon cycle, soil quality and sedimentation, and of course this is the burial term here, both on land and in the ocean, and human beings are trying to add to this burial through carbon capture and sequestration, which some models try to do as well. So in terms of modeling, often only land carbon cycle may be modeled with atmospheric exchanges, in which case there may be process studies looking at various aspects of how the fluxes and reservoirs are changing in response to warming. For example, changes in temperature and precipitation, changes in vegetation, changes in carbon uptake, and so on. Ocean carbon cycle also is often done separately to understand ocean circulation and how ocean is sequestering carbon and whether its sources and sinks are changing. So there is the idea of running carbon cycles with prescribed weather and climate or ocean circulation. And there is the idea of running the carbon cycle along with the climate model, the physical model, so call it the Earth system model then. There are the computational issues which we will look at and which we have looked at in the earlier parts, but adding carbon cycle can increase this cost by a lot. So there are uncertainties in the processes to be represented. For example, on land, photosynthesis and respiration happens by vegetation. But how do you prescribe vegetation? Do you prescribe them as fixed distributions, let's say observed over the last couple of decades by satellites? Or do you have a model that does what is called dynamic vegetation with C3 and C4 type photosynthetic pathways? Or do you do it by functional types like tropical forest, boreal forest, temperate forest, tundra, and so on? And similar issues exist in the ocean. Do you model them as functional groups of nitrogen fixing phytoplankton, diatoms, or you do it by size structure like nanoplankton, picoplankton, and macroplankton, large plankton, small plankton, including zooplankton and phytoplankton, who eats who, and predation, and so on. So constraining these models in terms of the rates of various things like photosynthesis and respiration, predation rates, grazing rates, mortalities, very, very complicated business. But what you can see is that even from the observational estimates, if you look at global carbon dioxide budgets in gigatons of carbon per year averaged over 2004 to 2013, I'm just taking this from the Berkeley site as an example, you can see that atmospheric growth, sources minus sinks, adds an uncertainty, so 4.3 plus minus 0.1. So measurements themselves have uncertainties. Ocean acidification, ocean sink is at 2.6 plus minus 0.8 gigatons. So the uncertainty is quite a bit higher here. And the contributions from deforestation and agriculture can have uncertainties that are more than 50%. And burning of fossil fuels is very well constrained, but then photosynthesis, land sink, can have a high uncertainty. So when you model these carbon cycles, you have to know whether the uncertainty is related to the deficiencies in the model itself, or the way the details are represented based on, let's say, satellite data used for land use, vegetation distribution, agricultural land, and so on. So amazing details, and yet we do a fairly good job of these things. This just shows again processes in terms of exchanges between terrestrial biosphere, volcanic inputs, atmospheric storage, and sources and sinks, organic and inorganic carbon moving from the land onto the ocean, and within the ocean the various processes. Ocean moves carbon up and down through circulation, which is called the solubility pump, and it also moves it through biology, like marine biota sinking and sequestering carbon, for example, which is called the biological pump. So ocean has to model both the biological pump and the solubility pump, and the biological pump has, of course, the uncertainties of how detailed the ecosystem representation is, how many phytoplankton you have, how many zooplankton you have, who's predating on the zooplankton, small fish, big fish, and so on. Plus there are uncertainties or model deficiencies in the circulation, because we don't know how the mixing happens. Winds may be wrong, ocean atmosphere interactions may be wrong, so all kinds of cascades happen, but you have to do the best you can. So here is another way to look at the whole carbon cycle again: human emissions from industrial activity and fossil fuel burning. So here you can see fossil carbon estimate is different, and there are various fluxes in and out, and the reservoirs in soil, carbon, atmosphere, ocean, and so on. But what is to be noted is that these numbers are large, so 90 in, 90 out. So you are looking at small changes in difference of two big numbers, so uncertainties can be high and estimations can be very difficult to make. So here you can see again 60 in, 60 out, and you have to estimate how much additional uptake is happening by land. So the carbon budgeting itself can be a nightmare. Plus, there are very different time scales. On long geologic time scales, carbon cycle is a stabilizing effect, in the sense if you warm the atmosphere, rainfall and humidity may increase, dissolution of CO2 increases, weathering rates increase, so carbon is drawn down from the atmosphere at geologic time scales. But when you look at glacial, deglacial time scales, we have talked elsewhere about how carbon dioxide increases when there is warming happening and glacier is melting, and that's an abrupt change because of the ice albedo feedback going fast in this direction. But carbon dioxide is a positive feedback, because as warming happens, glaciers melt, CO2 increases, CO2 traps more radiation, you have a positive feedback. And as glaciers build, which is a slow process, because as cooling happens, atmosphere cools, snowfall rates slow down, glacier buildup slows down, and CO2 decreases as temperature decreases, which means it's again a positive feedback, because decreased CO2 can again reduce the greenhouse effect and cool the temperature further. So it's a destabilizing positive feedback in one time scale, and a stabilizing weathering feedback on a long time scale. So these are just to give you a sense, just in words, how complex carbon cycle is and what are the various feedbacks that we have to consider. So when you do the projections for the future, often carbon cycle is done, but the carbon cycle feedback to the climate, as we talked about here, is not always done. Okay, so for example, there may be details missing in how vegetation distribution is changing because of warming and precipitation changes, because you don't have a dynamic vegetation model. You just are prescribing some distribution from the historic records and so on. So really complicated business, but we are far along in terms of improving the models, the processes, the parameters that are required to represent the rates as that I mentioned: photosynthesis, grazing, respiration, soil heterotrophic respiration, and so on. We are also good at estimating the feedbacks, because there are many models running with full feedback. So the Earth system models are getting better, and the physical aspect of it also includes how well they represent the sphere, which comes down to the resolution, grid resolution, which you have talked about before, but we will talk about it here again in the context of this Demystifying Climate Models by this book. Okay.